All right, so as always, I'm super tired, and we'll see how well I do because I'm tired. Okay, the space near Jupiter is not a very safe space. You need to be careful of protecting red spot, extreme radiation, and a whole lot of moons swirling around. You try to start tracking the four largest moons: Io, Europa, Ganymede, Callisto, pre-spanning the position of each moon. You need to simulate their motions so you can avoid them. Each moon is the three-dimensional position, the three-dimensional velocity. The position of each moon is given by your scan. The velocity starts at 0. Simulate the motions of the moon in time steps. Within each time step, first update the velocity of each moon by applying gravity. Then, once all moon's velocity has been updated, update the position of every moon by applying velocity. Time increases by one step and solve the to apply gravity, consider every pair of moons. On each axis, x, y, and z, the velocity of each moon changes by exactly +1 or -1 to pull the moons together. For example, if Ganymede has an x position of 3 and Callisto has an x position of 5, then Ganymede's x velocity changes by +1. Callisto's x velocity changes by -1. However, if the distances are the same, the velocity on the axis does not change. Once all gravity has been applied, apply velocity, simply add the velocity to each moon. For example, if Europe has a position of that. For example, suppose your scan reveals the following positions. Simulating. Then it might calculate the total energy in the system. The total energy is its potential energy multiplied by its kinetic energy. Potential energy is the sum of the absolute value of its coordinates. It's the sum of the absolute value of velocity. Blah 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 blah. The example above, adding together the total energy for all moons after 10 steps produces the total energy in the system, 179. Her second example. What is total energy for 1,000 steps? So let's think about this from typing import named tuple, same as always, and let's do xyz named tuple. X is an int, y is an int, z is an int, and let's say energy self goes to an int, and potential energy is the sum of the absolute values of its x, y, and z. Kinetic energy is the sum of the absolute values of its velocity. Return abs self plus x plus abs self dot y plus abs self dot z. Okay, and so that's good for x, y, z. And then let us say that class moon I'm trying to think about if I should use data classes, but I don't remember how they work, so I'm not going to. Def init self position xyz velocity xyz goes to none, and self dot position equals position, self dot velocity equals velocity. Okay, and so and now we can say we want to return so let's say potential energy self goes to int, return self dot position dot energy, and def kinetic energy self goes to int, return self dot velocity dot energy, and then def total energy. I'm probably being too cutesy by defining all these. Return self dot potential energy plus self dot kinetic energy. Okay, so now we have a moon, has position and its velocity, and now we want to apply velocity. Def apply velocity self goes to none, and so what I want to do is say self dot position equals xyz of self dot position dot x plus self dot velocity dot x, self dot position dot y plus self dot velocity dot y, self dot position dot z plus self dot velocity dot z. And then what I want to do is I want to def step moons, which is a list of moon, and it's going to step them in place, so it'll return none. And so what I want to do is first adjust velocity. I'll call it apply acceleration. First apply acceleration. So n equals len moons. This will be for I in range n, for j in range n if I not equal to let me just change this. For moon 1 in moons, for moon 2 in moons, if this is more indented than I like, if moon 1 is not equal to moon 2, then adjust the velocity of moon 1. If moon 1 dot position dot x is less than moon 2 dot position dot x, so to pull the moons together. So if that's the case, then let's say dx equals moon dot velocity dot x plus plus 1, L if moon 1 dot position dot x is bigger than moon 2 dot position dot x, dx equals moon dot velocity dot x minus 1, and otherwise the velocity doesn't change. So so now we need to do the same thing for y and for z. dy equals moon dot velocity dot y plus 1. Otherwise, if moon 1 has a bigger y position, change this to that. And then finally, this would probably be easier if I didn't use, I should learn how to use data classes, because I probably should have just done that and adjusted them in place. Let me just go do that. Python data class. So that's self.position.x plus equals self.velocity.x. So that's easier. And self.position.z equals self.velocity. Okay, so now I've gotten rid of this immutability, and so I can just do plus equals 1, moon 1.velocity.x minus equals 1, and so now I can do the same thing here, plus equals 1. So now I don't have to do, like in general I love immutability, but in this case, it's just getting in the way. So I'm just going to do it this way. So that's applying acceleration. And next, apply velocity. And now what I've done is I've said for moon and moons, moon dot apply velocity. So let's run day12.py and see what syntax errors I get. Named data class is not defined. From data classes, import data class. Okay, that's good. So now let's say moons equals the xy velocity of each one starts at 0. Equals xyz equals none, velocity or xyz 0, 0, 0. So that's fine. So moon is going to begin with -1, 0, 2, and 4 of them. And so then there's 2, 10, and -7, and 4, -8, and 8, and 3, 5, -1, and print moons. Actually, I don't even need to do that. And how many time steps do I have? I have 10 steps for n in range 10. Step moons, print moons. So let's run that and see what happens. Nothing happens because it was in all caps. And moon doesn't print itself nicely, so let's do this. Return moon self dot position velocity equals self dot velocity, and hopefully the data class will look nice. So after 0 steps is the initial. After 1 step, I have 2, 1, 3, 3, 1. Okay. So let's try this again. So we start off with -1, 0, 2, 0, 0, 0. Print n for moon and moons. Print moon. Do it that way; it'll be easier to read. It's possible I read the instructions wrong. That's always likely. So, this is the first one. For n in range 11, let's do that. Do it like this. Get rid of that, and clear. run it again. Okay, so we have minus 1, 0, 2, 0, 0, 0, 2, 10, 2, minus 10, minus 7, 4, minus 8, 8, and 3, 5, minus 1. So let's try it one more time. Okay, so I have 2 minus 1. Okay, so that's still wrong. Assuming that 2 minus 1, 3, 3 minus 1, 1. Okay, that's wrong. 3 minus 7 minus 4. That's fine. That's wrong. And that's wrong as well. So let's make sure I didn't read the instructions wrong. Consider every pair of moons. On each axis, the velocity and change. Pull the moons together. Gain means expedition. The three constants. Once all gravity has been applied, apply velocity. So we add the velocity of each moon to its own position. So this is minus 1. Its x velocity should be 3. Minus 1, 1, 1, 3, 3, minus 6. Okay, so let's think about this. It is going to get compared 3 times, and each time its velocity should only be okay, well that's probably the problem. Okay, 2 minus 1, 1, 3 minus 1, minus 1, 3 minus 7 minus 4, 1 minus 7, 5, 2, 2, 0. And after 10 steps, 2, 1 minus 3, 1 minus 8, 0. Okay. And let's do sum moon dot total energy for moon in moons is so because I applied it, did I apply it one more time? Too many times? Let's run it one more time. Because I stepped it again, and then no, but that's not right either. For moon in moons, print moon dot potential energy, print moon dot kinetic energy. 6, 6, 9, 5, 10, 8, 6, 3. Okay, so what? Print moon dot total energy. Because total energy is multiplying them, so that's another problem. $179. Okay, so that works. What is the total energy in the system after simulating the moons given in your scan for 1,000 steps? So moons equals moon xyz 0, 4, 0, moon xyz minus 10, minus 6, minus, what happens? Minus 10, minus 6, minus 14, moon xyz 9, minus 16, minus 3, moon, XYZ, 6, minus 1, 2. And I don't want to do this. Unexpected token, because I'm missing parentheses. Okay, and then for blank in range, and it said I think 1,000 steps. Is that right? 1,000 step moons. Print sum moon dot total energy for moon in moons. Okay, so let's run that, and I get 13,500. That looks like it's not the right answer, but let's try it. It is the right answer. Okay, good. Well, this drifting around makes this history your work. This moons will ever return to a previous state. Determine the number of steps that must occur before all of the moon's positions and velocities exactly match a previous point in time. For example, the first example takes 2772 steps for they exactly match a previous point in time, which returns the initial state. Okay, so let's do, we need something immutable that we can track. Self.position.x, self.position.y, self.position.z, self.velocity.x, self.velocity.y, self.velocity.z. Okay. And now def steps to repeat moons, which is a list of moon, and that's going to be an int, and do scene equals set, num steps equals 0, and let's set scene and let's make a new signature, which is moons, which is a list of moon, and we'll just return tuple moon dot signature for moon in moons. Scene dot add signature of moon. So let's go. Num steps equals 0, and so while true, num steps plus equals 1. Step moons sig equals signature moons. If sig in scene, return num steps, else scene.add sig. Okay, and now the first example takes 2772 steps. So, and I called that moons. So print steps to repeat of moons, and that should be 2772. That's good. Might last a very long time. Here's a copy of the second example. It takes this. Clearly, you might need to find a more efficient way to simulate the universe. How many steps does it take to reach the first state that exactly matches the previous state? So that's telling me that that this isn't going to work, basically. A more efficient way to simulate the universe. That's unfortunate. So that means we need to reason outside the system, which is the sort of thing that I'm too tired to do. But let's think about this. Clearly, you might need to find a more efficient way to simulate the universe. So this is one of those things where so you'd like to find a closed form for it, and so whichever one is so you sort of rank them, and you say whichever one is biggest. Let's see how many people have solved this so far. Both stars, 13 minutes. So that's a long time ago. Although only 35 so far. So that means it might be pretty hard. Although good for this guy. So let's think about this. It can't be very interesting to watch me flounder like this because I'm not writing code. I'm just sitting here staring at it. You might need to find a more efficient way to simulate the universe. So So let's think about this. One idea that I have is to see how long it takes. Everything operates independently, right? So one thing you could do is do the x's so for instance, what if instead of signature like this, I just change it to return self.position.x self.velocity.x, and I just see how long does it take for that to repeat. And maybe that will be faster. Let's see. Okay, so let me do let me change this a little bit. Sig x. So I'm making the assumption that basically x is going to repeat on some time frame, y is going to repeat on some time frame, and z is going to repeat on some time frame. And if we find the least common multiple of them, that that will give us what we want. And so again, I can do sig x moon dot sig x and do the same thing for y and z. So now so we'll pass in sig function now, and sig function, and so now what I want to do is I don't want to modify the moon, so import copy, and let's do the following. Moons equals copy dot deep copy of moons. So I think that'll work. Scene add sig function sig equals sig function of moons. Substitute moon sig x sig y and sig z. So let's try running that and see what happens. Not that this is necessarily any better, but this one goes after 286,000 steps. So import math. What is math G? Come on. I don't even know why this happened, but is it really that bad to type math G? I guess it is. Okay, so that's too many. Import math dot a times b divided by math dot GCD AB. AB equals this. AB times C divided by math dot GCD AB times C. And so that's way too long. So that doesn't divide by any of these, which is a problem. Oh, because that's not the stupid. So that's my answer, I think. That is the right answer. Okay, and I achieved rank 78 on the stars leaderboard again, 23 points. Good for me. So what did I do? I observed that what's going on in the x coordinate does not affect at all what's going on in the y coordinate. What's going on in the y, and let's see if that's the same as a times b times c. It is not. Okay, good. So so basically, if I find that the x coordinate repeats every 286,332 time steps, then that means every, like, once it gets back, it'll have 0 velocity and the same initial positions. So it's just going to repeat that. So every 286,332 time steps, the x coordinate will be back where it started. And then similarly, every 161,428 time steps, the y coordinate and velocity will be back where it started. And then finally, every 96,000 time steps, the c coordinate will be back where it started. Okay, so what that means is that in order to find when all three of them are back when they started, it needs to be a number that's divisible by all three of those cycle lengths, right? Because it has to be divisible by the first one so that a is back where it starts, and so on. And so because I want the first time it repeats, I need to find the smallest number that's divisible by each of those, which means it's the least common multiple. And now Python, I don't think, has a least common multiple function, but least common multiple of AB equals a times b divided by math.gcd, which it does have, of ab. I just happen to know that because it's like a math thing. And so if I do that in two steps, the first step I did, so for instance, I did, what did I call it? AB equals A times. So this is saying AB is is the smallest number that's divisible by both A and B. And so now I need a number that's, any number that's divisible by both A and B is going to be divisible by that number. And then I need a number that's divisible by C as well. So I do the same trick with A, B, and C, and then I get the right answer. Now, why don't I like this? The reason I don't like this is that because just because there's a long cycle doesn't mean that there's a short X cycle and there's a short Y cycle and there's a short Z cycle. There could be a long cycle because there's a really long X cycle and a really long Y cycle and a really long Z cycle. So like factoring out like this is not guaranteed to, I mean, it's not even guaranteed to find a quicker result basically. Like what if they all like were length 1 billion, each of them? Then the whole thing would be of length 1 billion as well. So that, like, it so happens that in this case, the X cycle is much shorter, the Y cycle is much shorter, and the Z cycle is much shorter. And so if you look for those, you'll find them and you can figure out what the longer cycle is. But there's no like reason why that has to be the case. And that's just kind of like me guessing and me saying, if I were writing an advent of code problem and trying to make it so that there was a trick to solving it, this is the problem I would make. But the issue is that like this trick doesn't necessarily work. It just happens to work because they chose a problem for which it works. And so there's something about that I find kind of, unsatisfying, that like I found a trick that worked, but it worked contingently rather than necessarily. And it was a little bit of me like doing the psychology of these guys. So anyway, I'm happy I solved it. I'm happy I got some points. I'm less happy about the fact that I was able to solve the problem this way, or that the problem was able to be solved this way. But that's life, and mostly I'm happy that I solved it. So anyway, that's enough of me ranting. So, all right, that's good. I will see you possibly tomorrow.